Hey everyone, welcome back to ML Works. In this video, we'll be continuing with our series on Visual Introduction to Deep Learning. And in the specific video, we'll be talking about how to build a neural network with linear regression. So we'll start off with a simple neural network as mentioned here, with one neuron taking only one input, which will generate one response, which is Y. And the dataset under consideration is a hotel room rate prediction where you have a feature called distance and you have a target variable price, and which is both of them are continuous number and can take any positive value. So we'll be assuming we have 10 data points and we'll be using 8 for training and 2 for testing purpose. So the goal would be to predict average daily room rate in a hotel based on the features, and the feature that we have is the distance. And since, as I mentioned earlier, so both are continuous value or number. So since target is continuous, we term the task as a regression task. So we have to predict the hotel price, which could be any numeric positive value. So we have to identify that based on the given input feature. So we'll have 8 data points whose distance we will be aware of, and then corresponding price. So we'll be taking 2 test data points for which price we don't know. Okay, so the idea would be to train a model. We have to predict for these 2 test data points and compare it with the actual ground truth. So let's assume this is the plot for the distance versus price. And if you see here, for around 8 data points, we have corresponding price. And then we have 2 data points for which we don't know what is the price. So what we do is we have to train a model such that we will be able to find a relationship between distance and price, and then we can use these 2 data points and test it out, those two. So on the x-axis we have distance in miles and price on the y-axis, which is in dollars. So based on our understanding, just by looking at the data, we can see there is a linear relationship between these two variables, which is distance and price. And the idea behind this linear relationship will be captured by the single neuron that we are building, or a neural network that we are building. So when it comes to training data, as I mentioned, we want to learn the relationship between distance and price with the help of 8 data points, and we'll be testing those relationships that has been learned on the 2 test data points. And in the previous video, we were discussing about the 4 steps of training, where we had predict phase, and then measure phase, then feedback, and then adjustment. Now we have already talked about data and task, where we have data in terms of distance is the feature, target is our price, training data set is where we have 8 data points, test data set is where we have 2 data points. Since the target is continuous number, we term the task as regression. Now since we are aware of all this information, now let's jump on to the 4 steps of training, which is predict, measure, feedback, adjust, and in neural network term, which is forward pass, loss function calculation, and then backward pass, and then weight update. So this is, you can see from the diagram itself, this is the forward pass, and you measure whether the ground truth is equal to the estimated output or predicted output, and then if the loss is high, then we go ahead and update the parameters as it is happening here in the cycle. Now let's talk about predict aspect of training. So we pass the training data through the neuron, and while we are passing it, the neuron will perform 2 operations, mathematical operations. One is weighted sum, and then there is activation. Weighted sum is nothing but it is a simple matrix multiplication and then addition of bias to that matrix multiplication. So we have distance, then we have weight, distance into weight plus bias, we get that output and send it through the neuron. Then we send it to the activation function. The activation could be any activation function, could be anything. It could be linear activation or non-linear activation like ReLU, or other different activation function. So before we go to the calculation aspect, just a point, number of weights is equal to number of inputs. Since we have one input, we can have only one weight. And number of bias will be equal to the number of neurons. So since we have only one neuron, we have one bias term. And how do we initialize these parameters, which is weight and bias? Basically, for this scenario, we'll be just setting it randomly. There are different ways with which you can be initializing the parameters. You can use any of these techniques, because these techniques will help you to avoid getting stuck in local minimum while you are trying to train the model over the number of epochs. So we'll talk about epochs as well later. So what is activation function? So once you have your input data multiplied with weight matrix and then adding the bias term to it, you will be passing that to the activation function. If it is a linear activation function, there will be no change in terms of the output that you get. It will be same as the input. Okay, so this is how the equation would look like. Now, during the predict phase, what we have seen till now will give you an output. So if you are passing the whole 8 data points, you will get 8 predicted values. And till now, we did not update any weights. Since it is randomly initialized, the model would not have learned anything yet. So let's now talk about measure in the training cycle. So in the previous step, we were trying to get the output from the neuron, and we got 8 predicted values. And what we can do is now we can use that 8 predicted values and compare with the ground truth and get the error value. So this is how you will be understanding whether your output is correct or not. So while we are doing that, we'll also talk about what is loss function, where you have these parameters called weight and bias, which will try to change the value of loss function. So there are different types of loss function. One could be, you can either use mean squared error, mean absolute error. So depending on the type of task you have, you can select your loss function. So in our case, we'll be using mean squared error. So we'll find the difference between predicted and ground truth and square them, and then have a calculation of average of all the 8 values. So the idea behind this mean squared error is to minimize the loss. So consider these 2 plots where you have on one plot the difference between the line and the data point is large. Okay, which means the calculation of MSC will result in higher value, and on the x-axis, as I mentioned earlier, we have distance and price. So this will result in higher MSC, and when it comes to this specific plot where the data is fitting to the line and only couple of data points are like having a higher margin of error, so what will happen is the total average MSC will be less compared to this specific plot. So now let's talk about feedback. In the previous 2 steps, we were discussing about prediction and measure, where we calculated the error value. Now what we'll do is we'll change the parameters, which is weight and bias, and see how it affects the loss function. So the idea is to ensure we have to update the weight and bias in such a way that the loss, which is MSC, is reduced to as low as possible. So consider we have weight on the x-axis, and then on the y-axis we have loss, and for a corresponding weight value you have corresponding loss function. So as you move towards either right or left, there will be some change in loss, and we want to ensure that it is less than the previous loss value. So what happens is, since we have around 8 data points, and the way we calculated the MSC is by squaring the value. So while after you square the value, you tend to have something like a curve for corresponding 8 weights, corresponding 8 loss values produced. When you plot those 8 points, you will be finding a curve like this. It may be different size or position, but you will find a curve. So the idea is to find a point in this curve where you will have the loss to be 0 or as low as possible. So as I mentioned, it could be differing. The curve can differ. Either it could be in this position or it could be in any other position. The curve can be much more highly sloped with a high slope it has. Okay, so it will differ, but it will be a curve, and you have to ensure that you update the weights, that is parameters, that you end up getting lower MSC. So let's now talk about gradient, because this will help you to understand how to update the weights such that we get the minimum MSC. So what is a weight gradient? First, let's define gradient, which is the derivative of output with respect to an input. So in our case, it is the weight as the input and output is our loss value or loss function. So if the curve is quite steeper than this one, like if you see this curve, it is less steeper than this curve. So when you have such scenario, what happens is the gradient that we are measuring, it refers to the steepness of the curve. So the steeper the curve is, the greater the gradient is. So we want to update the weights by a larger value such that we can reach the optimal point or minimum MSE. So that's the idea behind the steepness. Now the ideal scenario is where you have gradient is equal to 0 and which brings the MSE to the bottom of the curve. Now there are two properties of a gradient. First is magnitude, which will tell you by how much amount or by how far the predicted value is from the actual value. So which will also tell us by how much amount you have to update your gradient or the weight. Okay. The second property is the direction, from which direction you have to move down towards the optimal value. So suppose the starting weight is on the other side of the curve, which is on this side, which is the negative side of a axis. Okay, this causes the sign of the gradient to be negative, as I said. So this indicates the gradient is too small rather than high, and instead of decreasing, we have to increase the weight. So if your weight was here, okay, on this side, then you have to decrease your weight such that you have to move down this side. But if your weight is on this side, okay, and then you have to increase your weight such that you move towards this direction. So this informs the direction in which the gradient has to move such that we can reach the minimum or optimal value. Now this movement of this gradient value downwards is called gradient descent. So if you see here, magnitude and direction of a weight gradient are two types of feedback returned to the network. So these are kind of a feedback that we are talking about. So as the network goes through multiple training cycles, we want the weight to move down the curve towards its minimum point. So if first initially the steepness will be there, okay, as you move towards down, either from this direction or this direction, the steepness will reduce and we finally will have a point which is minimum, such that we'll have MSE also minimum. Now let's talk about weight gradient, which means gradient refers to derivative of the loss function with respect to weight. And when we want to update a previous weight with the updated weight, what we have to do is we have to calculate something called as DW, which is nothing but input into error. And what we have to do is for all the training points, we'll be calculating DW. Okay, and we'll create an average value. We'll find the average value, and that is your final gradient value that needs to be updated to the existing weight. So that's called adjust step or update step, and this is the final step of the training cycle. So while we are doing that, we also have to make sure we are including learning rate, which will help you to stabilize the flow of the gradient descent. Okay, so if the gradient is positive, meaning dW is positive, then what you have to do is you have to move it towards the negative side. That is, we have to reduce the weight. That's what's given here. The previous weight is reduced. And if the gradient is negative, which is in this case, we have to move it towards positive. We have to increase the previous weight. So we have to move it this direction. So here we bring in a new term called as learning rate, which is represented by alpha, and it is multiplied with gradient. So how do we update it? So we take something called as W new is equal to W previous minus alpha into dW, which is the gradient into learning rate and minus with previous weight. Now, as I said, what happens when you have learning rate or not? To smoothen the gradient descent, we include learning rate. So if you don't add or include learning rate, what will happen is the gradient won't move down. Okay, so it may take time to either get to the minimum, optimal minimum, or there are chances that it may not even get down here at the minimum value. So that's why we want to include learning rate while you're calculating updated weights. Otherwise, if you have learning rate, there is a very good chance you will be smoothing down the gradient descent as shown here. Now let's talk about bias. Till now what we have seen is how we are updating the weights. Now we want to talk about how bias is updated. So the whole reason we include bias is to ensure we change the function, right? Adjust the position of the function. The objective function that is being learned by the model is adjusted in terms of position with the help of bias. So if you see here, when we are updating the weights, we are trying to change the position of the line like this, like in the curve nature, right? This nature of the line is moved like this. When we are updating the bias, we are shifting it up and down. Okay, that's the main difference between weight and bias. So now let's talk about bias gradient. We get the bias gradient by calculating the derivative of the loss function with respect to bias. Earlier it was with respect to weight. Now which is basically means error. So unlike while we are updating or getting the gradient for weight where we used input into error, for bias what we have to do is we just have to take the error value. So next what we do is we adjust the bias, the previous bias value, by taking in the new gradient into multiplying it with the learning rate. And similar to weight updates, here also what we do is if dB is positive, then we move towards negative side, and if it is negative, then we move towards positive side. Now this is what adjustment we have to do, and this is the end of how we update the bias. And with this what we do is we complete one cycle iteration of data set throughout this 4 components of training. So what we have done is we have taken the data, now we have predicted it, then we calculated the MSC where we found the average value of the MSC, and then what we did is we updated the weight, and then we updated the bias. This is these 2 steps we have done. Now what we have to do is, since we have done it for one complete epoch, if you have 100 epochs, we have to pass the data set 100 times, we have to update the weight 100 times. And by that time we'll also be calculating the MSC. It has to reduce by 100 epochs. If it is not, then we have to look into other aspects of neural network training. Now while we are training this for 100 epochs, we have to notice as the epochs are increasing whether the MSC is decreasing or not. So in our scenario, both cost and metric will look similar, and it will reduce as we are training it for 100 epochs. Now once we calculate for after 100 epochs for training performance, we see MSC of 16.4. Once we have trained the model, then what we have to do is we have to store it, and then we have to predict it for the 2 test points that we have discussed earlier. Now when it comes to testing, what we do is instead of going through the 4 points of the cycle like predict, measure, feedback and adjustment, what we do is we just do predict and measure, and we pass in the 2 points, predict it, measure what is the error, and get the final result. So when we do it for our data set, what we see is for those 2 data points resulted in MSC of 68.4, which is less than what we saw for training performance. So yeah, with this we'll be concluding this video. Thank you for watching.